Next, we will study Heine Borel Theorem and boundedness and uniform continuity of compact sets. So first of all, we will study Heine Borel Theorem for the set of real numbers. Suppose we denote the set of closed and bounded interval AB in the set of real numbers by J. Then any open cover of this closed interval AB admits a finite subcover, that is AB is compact. Closed interval AB is compact. We know by the definition of compactness that a set is said to be compact if its every open cover admits a finite subcover. Suppose this theorem is false, means any open cover of AB does not admit a finite subcover. Suppose we assume that UI, where I belongs to some indexing set, is an open cover of the set of closed interval AB, and we assume that it does not admit a finite subcover. So in the proof of this theorem, we bisect this interval AB, which we have denoted by J, and we observe that the open cover UI, where I belongs to I, does not admit a finite subcover for one of the sub-intervals. When we divide this J, we call the sub-interval by J1, and we repeat this argument, replacing J by J1, J1 by J2, J2 by J3, and so on. In this case, we will have nested sequence Jk such that Ui, here it is I also in the suffix, Ui, I belonging to I, does not admit a finite subcover for any of Jk's. If C belongs to intersection of K, Jk, then C belongs to U alpha for some alpha belonging to I, because C is in the intersection of Jk, and this is a open cover of J. Now we show that Jk is a subset of U alpha for all sufficiently large values of K. So we bisect the interval J equal to AB like this. One subinterval is A to A plus B upon 2, and another subinterval is from A plus B by 2 to B. So we have bisected J into two subintervals, and clearly this J is equal to now A to A plus B upon 2 union A plus B upon 2 to B. We notice that Ui, where I belongs to I, is an open cover for each of these subintervals. Now we claim that this does not admit a finite subcover for any of these subintervals. Suppose it assumes finite subcover. Suppose in this case the first interval A to A plus B upon 2 is covered by the unions of UI1, UI2 and UIM, and second subinterval, which is from A plus B upon 2 to B, is covered by UJ1 union UJ2 union UJN. Then in this case our interval AB is a subset of union of these covers, means UI1 union UIM union UJ1 union UJN, because this open interval is a union of two subintervals, so this is covered by these covers. Thus it means this open cover admits a finite subcover for AB. But this is a contradiction to our hypothesis, because we have assumed that this open cover does not admit any finite subcover for interval AB. Hence the claim follows. Now we select one subinterval for which Ui has no finite subcover. We denote it by J1 equal to A1 to B1, and we notice that A is less than or equal to A1 because A1 is equal to A, and or A1 is equal to A plus B by 2. And we observe that this open cover does not admit a finite subcover. For J1, the length of this interval J1 is B1 minus A1, which will come out to be B minus A upon 2. The left end point of point A1 of J1 is greater than or equal to that of J, that is A is less than or equal to A1. We repeat the argument replacing J by J1 because Ui, where I belongs to some indexing set, is an open cover of J1 admitting no finite subcover for J1. We then obtain a subinterval J2 which is equal to closed interval A2 to B2 of J1 such that Ui, where I belongs to some indexing set, does not admit finite subcover. For the given cover, the length I of J2 is equal to B2 minus A2, which will come out to be B1 minus A1 upon 2. And if we substitute the value of B1 minus A1 was B minus A upon 2. So B minus A, if we substitute B minus A upon 2, we will get 2 raised to power minus 2, because it is that in that case it will be 2 square, and this is B minus A. So 2 raised to power minus 2 B minus A. The left hand of A2 of J2 is greater than or equal to that of J1, that is A1 is less than or equal to A2. We repeat these steps again and again, and we get a sequence of subinterval Jk with the following properties. Means this cover does not admit a finite subcover for Jk for any k belonging to n. The length of interval Jk is Bk minus Ak, which will come out to be 2 raised to power minus k into B minus A, like this. And the left end point of Ak of Jk is greater than or equal to that of Jk minus 1, that is Ak minus 1 is less than or equal to Ak. We have drawn the figure here. So it is Ak, it is Bk. C is the point in between Ak and Bk, and this is in the neighborhood of C minus epsilon and C plus epsilon. So if we consider the sequence Ak, it is a non-decreasing sequence of real numbers. It means Ak plus 1 is greater than or equal to Ak for all k belonging to n. Also it is bounded for all Ak belonging to closed interval AB. It means from a standard result from real analysis, the sequence Ak converges to C, which is equal to supremum of these Ak. And we observe that this C belongs to closed interval AB. This is the point C. For C is an upper bound for all Ak, and in particular C is greater than or equal to A1, which is greater than or equal to A. Also C is the least upper bound for the set Ak, where k belongs to n, and B is its upper bound, hence A is less than or equal to C is less than or equal to B. Now we claim that our sequence Bk converges to C. Let's see. We know that modulus of Bk minus C is less than or equal to Bk minus Ak plus Ak minus C by triangle inequality of metric space. And this is the length of interval Ak to Bk, so which was 2 raised to power minus k into B minus Ak A, and this is Ak minus C. And we know that Ak tends to C, and it means this tends to 0 because 2 raised to power k minus k tends to 0, and it follows from the observation that k is less than 2 raised to power n for all k belonging to n, and 2 raised to power minus k is less than 1 upon k. So this tends to 0 as k tends to infinity. Since C belongs to closed interval AB and this is an open cover of AB, there exists alpha belonging to I such that C belongs to U alpha. Since U alpha is open, there exists epsilon greater than 0 such that C minus epsilon to C plus epsilon is a subset of U alpha. Since AK tends to C and BK tends to C, there exist positive integers k1 and k2 such that ak belongs to the open interval c minus epsilon to c plus epsilon for k greater than or equal to k1, and bk belongs to c minus epsilon to c plus epsilon for k greater than or equal to k2. If k is greater than or equal to k naught, where k naught is maximum of this k1 and k2, then ak and bk belongs to c minus epsilon to c plus epsilon, and therefore the closed interval ak to bk is a subset of this open interval, which is again a subset of u alpha. It means this set ui admit a finite subcover for jk if k is greater than or equal to k naught, but this contradicts the assumption on jk, because here it is mentioned that this open cover does not admit a finite subcover for jk for k belonging to n. So here we get the contradiction. This contradiction shows that our original assumption that ui I belong to I does not admit a finite subcover for j is wrong. Hence the theorem follows. So we have proved that by assuming the contradiction that any open cover of closed interval AB does not any open cover of closed interval AB admits a finite cover, that is AB is compact. So this contradiction shows that our original assumption that does not admit a finite subcover for J is wrong. It means it will admit a finite subcover. It means the closed interval AB, which we have denoted by J, is compact. Now next lemma is the square S equal to closed interval minus R to R, and whose length is minus R to R and breadth is minus R to R is compact subset of R square. We follow similar step in proving this lemma also. In this case we have a square, so we keep dividing the square into smaller squares to get the result. Suppose S is not compact, we have assumed a contradiction, then there is an open cover ui of which there is no finite subcover of S. So we divide the square S into 4 smaller squares by joining the pairs of midpoints of the opposite side. So here is the diagram. This is the main square. So we divide this square by joining the midpoints of opposite sides of a triangle. So we have divided into 4 squares, 1, 2, 3 and 4. In the second step also we divide one of the square into 4 parts, 1, 2, 3 and 4. In third step also we divide the square into 4 squares, and we repeat this process till we get the result. So suppose one of these square will not have a finite subcover from the given cover, because we have assumed that S is not compact. For otherwise each of these square will have finite subcover, so the union of these subcovers will be a cover for S. Thus S itself will admit a finite subcover. Choose one such smaller square and call it by S1. Note that the length of its sides is R, and if A1 C1 is the bottom of left vertex of S1, then A1 is greater than or equal to A0, which is equal to minus R, and C1 is greater than or equal to C0, which is also minus R. We repeat the argument of subdividing S1 into 4 square and choosing one of the smaller square which does not admit a finite subcover of ui, where I belong to some indexing set. We call this smaller square as S2. We know that length of its side is R upon 2. And if A2 C2 is the bottom vertex of S2, then A1 is less than or equal to A2 and C1 is less than or equal to C2. So this is the figure. Proceeding these steps again and again, we have a sequence of squares Sn such that Sn does not admit finite subcover, and length of side of S is 2 raised to power minus n plus 1 into R, and its bottom left vertex is An Cn, and it is such that An minus Cn is less than or equal to An, and Cn minus 1 is less than or equal to Cn. Here it is A1 C1, here it is A2 C2, and here it is A3 C3. Thus we have two sequences of real numbers. One is A1 An and another is Cn, and these sequences are bounded and monotone. Hence there exist real numbers A and C such that An tends to A and Cn tends to C. It means the open interval A and Cn tends to open interval AC, which belongs to two-dimensional real space. Since S is closed, AC belongs to S. Hence UI0 is the open cover such that AC belongs to U10. Since U10 is open, there exists an R greater than 0 such that ball centered at AC and radius R is a subset of U10. Here 0 is in the suffix of 1. Choose n belongs to n with the following properties. Diameter of S1 is equal to 2 raised to minus n plus 1 under root 2 into R, and this is less than R by 2. Number 2, the distance of open interval AC to open interval A and Cn is less than R by 2. In this case we have, for any xy belonging to Sn, distance of AC from xy is less than or equal to distance of AC from A and Cn plus distance of A and Cn from xy. This is by triangle inequality of metric space. We know that this distance is less than or equal to R by 2, and this distance is less than or equal to 2 raised to minus n plus 1 under root 2 into R. So this is obviously less than R. It means Sn is a subset of ball centered at AC and radius R, and this is contained in U10. But U10 is a finite subcover for Sn, which contradicts the choice of our SKs, means our choice of our squares. Therefore our assumption that S is not compact is not tenable. It means the square S, which is defined like this, is a compact subset of R square. We can extend our Heine Borel theorem for the set of real numbers to n-dimensional case also. A subset Rn is compact if and only if it is closed and bounded. Now one more result. A continuous function on a compact metric space is bounded. If a set is compact, then any continuous function on it is bounded. Suppose y is equal to set of real numbers or set of complex number. If y belongs to capital Y, then for each n belonging to n, the set Byn, which is a ball centered at y and radius n, is open set in y. Hence un equal to f inverse of Byn, which is nothing but x belonging to x, such that d distance of fx from y is less than n is open. Notice that un is a subset of un plus 1. So the collection of these un, which we have defined like this, which is the inverse image of this ball, is an open cover of compact space X. If U and I, where I lies between 1 mm, is a finite subcover, and if n is equal to maximum of these ni's, then x is equal to un. That is, f of x is equal to f of x is a subset of ball centered at y and radius capital N. It means fx is bounded, or we can say that continuous function on a compact metric space is bounded. Now the continuity, uniform continuity. Suppose xt and yd dash be metric spaces. A function f from x to y is called uniformly continuous if for every epsilon greater than 0 there exists a delta greater than 0, such that if xy belongs to x and distance of x from y is less than delta, it means distance of fx from fy is less than epsilon. These distances are taken with respect to this metric space, and this distances have been taken with respect to this metric space because f is a mapping from x to y. With respect to x we have metric d, with respect to y we have metric d dash. Now one more theorem: any continuous function from a compact metric space to another metric space is uniformly continuous. Suppose f is a mapping from x2 to y be continuous, and suppose x is compact. Now we need to prove that f is uniformly continuous. So because f is continuous, given epsilon greater than 0, there exists an rx greater than 0 such that distance of x from y is less than rx, implies distance of fx from fy is less than epsilon by 2. So instead of the open cover B of balls centered at x and radius rx, where x belongs to x, we consider the open cover bx with radius rx upon 2, where x belongs to x, and apply compactness. Here instead of rx we have considered it rx by 2. Let bxi ri upon 2, here radius is ri upon 2, be a finite subcover. Here ri is equal to rx and I lies between 1 and m. Let delta is equal to minimum of these ri by 2, where r lies between 1 and n. Let x phi belongs to x be such that distance from x to y is less than delta. Now if x belongs to this ball centered at xi and radius ri by 2 for some I, then we see that distance of y from xi is less than or equal to distance of y from x plus distance of x from xi. This is by triangle inequality, but distance of y from x is less than delta from here, so it is delta. And distance of x from xi, because x is a point on this ball, so it means distance of x from xi is less than ri by 2, ri upon 2 is its radius, so it is ri upon 2, and this is less than ri. Because distance of y from xi is less than ri, it means y belongs to a ball centered at xi and radius ri. Now again using the triangle inequality we get distance of fx from fy is less than distance of fx from xi plus distance of fxi from plus fy. This is less than epsilon by 2 plus epsilon by 2 by our choice of ri. It means by the definition of uniform continuity, f is uniformly continuous, because for whenever dxy is less than delta, we have proved that distance of fx from fy is less than epsilon, because epsilon by 2 plus epsilon by 2 is nothing but equal to epsilon, we can write it here equal to epsilon. So now what is finite intersection property? Let X be a set. We say that collection A of non-empty subsets of X has finite intersection property if every family A1, A2, An of elements in A has finite intersection property. Now sequentially compact. A metric space Xt is called sequentially compact if every sequence in X has a convergent subsequence. A subset Y of X is called sequentially compact if the metric space Yd dash is sequentially compact. Now sequentially continuous. A function f from x to y is sequentially continuous at a belonging to x if xn tending to a implies fxn tends to fa in y. Xn tends to a is in x and fxn tends to fa is in y, because fxn is the image of xn under f and fa is the image of a under f in y. Now what is Bolger-Weierstrass theorems? Let X be an enclosed bounded subset of the real line are sequentially compact, then any sequence xn of points in X has a subsequence converges to a point of X. Thank you.